What if the history of our universe was fundamentally different from what we have been taught for generations? What if the earliest chapters of cosmic time were not filled with simple, primitive gas clouds, but with highly organized, mature, and hyper-efficient structures that challenge our most advanced models of reality? For decades, astronomers operated under a clear, elegant timeline. We believed that after the energetic flash of the Big Bang, the cosmos underwent a slow, gradual awakening. It was a linear story where gravity spent hundreds of millions of years gently pulling matter together, slowly coaxing the first simple stars out of the pristine darkness. We expected that the earliest galaxies would be small, fragile, and chemically pure fragments, possessing almost none of the heavy elements required to build complex planets or support life. But when humanity launched its most precise infrared observatory into the cold vacuum of space, that comfortable, gradual narrative began to shift. By looking deeper into the infrared dark than any instrument before it, the James Webb Space Telescope opened a window onto a deeply unfamiliar past. Instead of a quiet, simple cosmic infancy, it revealed an era of astonishing complexity, rapid chemical maturity, and high energy efficiency. Imagine peering back 13 billion light-years and discovering massive, mature stellar systems operating like cosmic factories at production rates that seem to accelerate past conventional timelines. Imagine finding supermassive black holes already weighing millions of solar masses within the first few hundred million years of existence, consuming surrounding matter at rates that stretch the limits of modern astrophysical calculations. These are not isolated errors or simple anomalies that can be easily dismissed. From the deepest structural threads of the intergalactic web to our immediate cosmic neighborhood, a rich series of discoveries is forcing researchers to refine their models of the ancient universe. We are finding pairs of free-floating, Jupiter-mass worlds drifting through star-forming nebulae while broadcasting unexpected radio signatures. We are witnessing ultra-short-period exoplanets maintaining volatile-rich secondary atmospheres while orbiting so close to their parent stars that their rocky surfaces exist as oceans of molten magma. We are observing early, massive stellar systems that unexpectedly halted their star formation altogether, entering a state of deep cosmic hibernation when they should have been at the absolute peak of their creative growth. This is not a story about a broken universe, nor is it a declaration that our fundamental physics has failed. Rather, it is a journey into a historic golden age of discovery. It is an exploration of how modern observations are adding vital new layers of complexity to our understanding of cosmic history, revealing that the early universe was far more dynamic, interconnected, and efficient at organizing matter than we ever imagined. To understand why recent space telescope observations are causing such a profound stir in the astronomical community, we have to look closely at the foundational models that have guided astrophysics for the past several decades. Cosmologists rely heavily on what is known as the Standard Model of Cosmology. This framework acts like a master blueprint for the universe, detailing how much normal matter, and dark energy exist and how they should interact over billions of years. According to this blueprint, the universe is supposed to grow in a highly methodical, step-by-step fashion. To visualize this, imagine building a massive city. You do not start by instantly dropping fully formed skyscrapers into empty fields. Instead, you begin by grading the land, laying down small concrete foundations, building single-story homes, and slowly expanding outward into interconnected networks over a long period. In the standard cosmological model, gravity plays the role of the master builder, and it is restricted by a strict speed limit. After the energetic event of the Big Bang, the universe was filled with a nearly uniform, hot soup of hydrogen and helium gas. For stars and galaxies to form, gravity had to slowly draw these scattered gas molecules together into denser clouds. This initial compression takes an immense amount of time. Astrophysicists use a concept called redshift to measure just how deep into the cosmic past we are looking. Because the universe is continuously expanding, light traveling across the vast gulfs of space gets stretched out over time. By the time the light from an ancient, distant object reaches our detectors, its short, energetic wavelengths have been pulled into longer, less energetic infrared wavelengths. The greater the distance an object's light has traveled, the higher its redshift value, and the further back in cosmic history it resides. For a long time, our view of this high redshift universe was severely limited. Older observatories, like the legendary Hubble Space Telescope, viewed the cosmos primarily in ultraviolet and visible light. While Hubble revolutionized our understanding of the universe, the light from the very first stars and galaxies had been stretched so far by cosmic expansion that it shifted entirely out of Hubble's optical range and into the infrared spectrum, rendering those early structures virtually invisible. The launch of the James Webb Space Telescope completely changed the rules of the game because it was specifically engineered to be an untargeted, hypersensitive infrared time machine. Equipped with a massive, gold-coated primary mirror and advanced mid-infrared and near-infrared spectrographs, this observatory can capture the highly stretched, ancient light that has been traveling across the void for over 13 billion years. Spectroscopy is the scientific process of breaking light down into its component colors, much like a prism separates sunlight into a rainbow. By analyzing the specific lines within a spectrum, astronomers can decipher exactly what an object is made of, how fast it is moving, and how massive it truly is. When these powerful infrared instruments were finally pointed toward the earliest epochs of cosmic history, they ran directly into the core scientific problem we face today. The telescope began detecting massive, highly luminous galaxy candidates and incredibly energetic black holes at high redshift levels, corresponding to just a few 100 million years after the Big Bang. According to the classical hierarchical assembly models, there simply should not have been enough time for gravity to gather that much matter together, let alone organize it into dense, structurally mature environments. This presents theoretical physicists with a monumental puzzle. If these early objects are as massive and structurally advanced as the initial data suggest, then our understanding of the early universe's efficiency must be incomplete. It means that either matter was able to clump together much faster than our computer simulations ever predicted, or some unrecognized physical mechanism was actively speeding up the crystallization of structure in the early cosmos. Furthermore, this mismatch scales up to the largest structures in existence, manifesting as a profound discrepancy in the cosmic expansion rate, known as the Hubble tension. When astronomers calculate how fast the universe is expanding by looking at the ancient, pristine light of the cosmic microwave background, which is the leftover radiation from the early plasma universe, they get one specific value. But when they measure the expansion rate using local, modern cosmic indicators, such as pulsing Cepheid variable stars and distant Type 1a supernovae, they consistently get a significantly higher expansion rate. The precision of our newest observatories has effectively ruled out simple calibration or measurement errors. The tension is real, and it suggests that our standard cosmological blueprint might be missing a fundamental piece of the puzzle. We are left looking at a universe that appears to organize its matter with an unexpected, hyper-efficient velocity, while expanding at rates that continuously challenge our linear calculations. To bridge the gap between theoretical models and reality, we must examine the specific, verified observational evidence gathered by our most precise space observatories. This data provides a detailed, empirical look at how the early cosmos operated, replacing speculation with hard astrophysical facts. The first major line of evidence comes from deep spectroscopic surveys, targeting the most distant galaxies ever observed. A primary example is a high-redshift galaxy designated Jades-GS-Z14-0. Discovered during an extensive deep-field campaign, this pristine stellar system is seen as it existed less than 300 million years after the Big Bang. When astronomers broke down its light using infrared spectrographs, they expected to find a faint, poorly organized smudge of pure hydrogen and helium gas. Instead, they detected a highly luminous, extended galaxy spanning over 1,600 light-years across. More surprisingly, the spectral signature revealed clear, unmistakable lines of oxygen and dust. For oxygen to exist in such abundance so early in cosmic history, an entire generation of massive stars must have already formed, lived their brief lives, fused lighter elements into heavier ones within their nuclear furnaces, and distributed those elements into the surrounding space via catastrophic supernova explosions. This proves that early chemical evolution did not crawl, it sprinted. Alongside these surprisingly mature early galaxies, astronomers have identified a ubiquitous population of compact red objects colloquially known as little red dots. When first discovered in deep-field images, these objects appeared as tiny crimson pinpricks of light. Through careful multi-wavelength analysis, researchers have determined that these little red dots are incredibly dense systems existing within the first billion years of the universe. The intense infrared light they emit means they are either exceptionally tightly packed clusters containing hundreds of millions of mature stars, or they are dust-enshrouded active galactic nuclei powered by central black holes. If they are driven by black holes, it implies that the early universe was heavily populated with compact gravitational monsters far earlier than anyone predicted. This leads to the verified evidence regarding early black hole growth, which has completely reframed the physics of cosmic feeding. For a long time, scientists believed that a black hole was strictly limited in how fast it could consume matter. This barrier is known as the Eddington limit, a physical balance where the outward pressure of the light generated by superheated, infalling gas pushes back against the inward pull of the black hole's gravity. If a black hole tries to swallow matter too quickly, the intense radiation pressure should theoretically blow its food supply away, capping its growth rate. However, recent observations of an early active galactic nucleus designated LID-568 have shattered this perceived speed limit. Located just 1.5 billion years after the Big Bang, this supermassive black hole was caught undergoing an extreme super-Eddington accretion. The data revealed that LID-568 is actively devouring surrounding gas at roughly 40 times its theoretical Eddington limit. It is the astrophysical equivalent of forcing water from 40 separate fire hoses down a single narrow pipe simultaneously without bursting the Schrem apparatus. This discovery provides a verified mechanism explaining how high-redshift black holes could have grown to supermassive status so rapidly. They did not rely on slow, steady accumulation, but instead engaged in violent, hyper-efficient feeding frenzies that bypassed standard structural constraints. Moving from the high-redshift universe to unique localized environments, modern infrared astronomy has revealed structural anomalies within star-forming regions much closer to home. In the Orion Nebula, the James Webb Space Telescope uncovered dozens of enigmatic entities known as Jupiter Mass Binary Objects, or JUMBOs. These are free-floating planetary mass objects that do not orbit any parent star. Instead, they drift through interstellar space in pairs, orbiting one another at distances ranging from 25 to 400 times the Earth-Sun distance. According to standard models of star and planet formation, gas clouds shouldn't be able to collapse into objects as small as Jupiter on their own, and planetary systems shouldn't easily eject intact pairs of planets into the void. To deepen the mystery, sensitive radio telescope surveys have detected faint, high-frequency gigahertz radio signatures originating from some of these binary pairs, indicating that they possess complex, dynamic magnetic fields interacting as they dance through the eternal dark. A similar theme of unexpected environmental resilience is seen in the ultra-short period rocky exoplanet 55 Cancri e. This extreme world orbits its host star so closely that a full solar year lasts a mere 18 hours, and its dayside temperature exceeds 4,000 degrees Fahrenheit, transforming the surface into a vast ocean of churning liquid magma. By all the classical laws of planetary science, the intense stellar winds and high-energy radiation from the nearby star should have stripped away any envelope of gas within millions of years, leaving the planet as a barren, airless rock like Mercury. Yet, when astronomers measured the planet's thermal emissions, they discovered that the day side was noticeably cooler than expected, meaning some insulating layer was actively distributing the star's heat around the globe. The verified spectroscopic data indicates that 55 Cancri e maintains a thick, volatile-rich secondary atmosphere composed primarily of carbon monoxide and carbon dioxide. This atmosphere is not a remnant from the planet's birth. Rather, it is a secondary shroud continuously bubbled up and replenished by the degassing of the immense global magma ocean below. The planet's molten interior is actively feeding its impossible sky. Finally, Mapping the largest scales of cosmic architecture has revealed that these localized systems are embedded in a highly organized macrostructure. By measuring the polarization of light traveling through intergalactic space, researchers have mapped extensive magnetic fields threading directly through the vast gas filaments of the cosmic web. These magnetic networks display a high degree of structural connectivity, mapping out the voids and clusters of the universe in intricate patterns. This proves that magnetism was not a late byproduct of galaxy evolution, but an ancient structural force that helped guide the distribution of matter from the very beginning. The verified observational data collected from our newest generation of space observatories do not simply add new entries to astronomical catalogs. They force researchers to test old assumptions and rethink the fundamental timelines of cosmic evolution. When we find systems like the high-redshift galaxy JADES-GS-Z14-0 or super Eddington feeders like LID-568, we are confronted with empirical proof that the early universe was vastly more efficient at transforming raw gas into highly structured systems than our classic models allowed. For decades, the prevailing narrative of cosmic architecture was built on the concept of hierarchical structure assembly. This theory assumed that the universe grew slowly and cautiously. Small clumps of dark matter and pristine gas would gradually merge to form tiny, primitive star clusters. Over billions of years, these small clusters would collide and combine to form dwarf galaxies, which would eventually merge to form massive spiral and elliptical structures like our own Milky Way. It was a comfortable, slow-paced model that timeline calculations could easily accommodate. However, the discovery of highly luminous, structurally advanced galaxies and hyperactive black holes existing within the first few 100 million years suggests that our picture of the early universe requires significant refinement. These discoveries challenge existing models by showing that the universe was capable of achieving a high degree of organization and chemical maturity almost immediately after the cosmic dark ages. Instead of a slow building process, the early cosmos appears to have experienced a period of rapid, accelerated structural crystallization. This forces theoretical physicists to reconsider the role of dark matter in the early universe. Dark matter acts as the invisible gravitational scaffolding of our cosmos, providing the gravitational pull necessary to draw normal gas together into stars and galaxies. If massive galaxies and supermassive black holes formed so quickly, it suggests that dark matter may have clumped together far more rapidly or intensely in the early epochs than previously assumed, pulling normal matter along with it in a highly accelerated cosmic dance. Furthermore, these discoveries open a completely new research direction regarding the coevolution of galaxies and black holes. In the modern universe, there is a well-established proportionate relationship between the mass of a galaxy's central supermassive black hole and the total mass of the stars within that galaxy. They appear to grow together in a delicate balance governed by active galactic nucleus feedback, where the energy emitted by a feeding black hole periodically blows away excess gas, regulating both its own growth and the birth rate of new stars. But the high redshift data reveal an environment where this balance was heavily skewed. We are observing early systems where the central black holes are disproportionately massive compared to their host galaxies, sometimes making up a significant fraction of the system's total mass. This structural mismatch suggests that black holes did not slowly grow alongside their host galaxies over eons. In many cases, the black holes got a monumental head start. Bypassing the standard evolutionary steps, these early gravitational monsters may have acted as the primary anchors around which the first massive galaxies were organized. This matters profoundly because it changes our understanding of the cosmic chemical timeline. If multiple generations of massive stars were living, dying and distributing heavy elements like oxygen, carbon, and iron within the first few 100 million years, then the chemical ingredients necessary to build solid rocky cores and complex chemical networks were present far earlier in cosmic history than anyone anticipated. The early universe was not a sterile, uniform void of pure hydrogen. It was a highly dynamic, chemically rich environment that was rapidly synthesizing the building blocks of structural complexity. Ultimately, these observational insights demonstrate that our science is working exactly as it should. When new, hyper-precise technology provides data that contradicts older theoretical expectations, it does not mean that physics is broken. It means we are on the verge of a deeper understanding, forcing us to revise our equations, expand our computer simulations, and develop more nuanced models that can truly capture the hyper-efficient complexity of the ancient cosmos. When we step back from the individual data points, telescope metrics, and specific high-redshift designations, these discoveries connect directly to the grand unfolding story of our universe. They reveal that the cosmos, from its very earliest moments, possessed an extraordinary capacity for self-organization, shifting from a uniform sea of energy into a highly structured network of stars, galaxies, and planetary systems with astonishing velocity. Every heavy element we detect in a distant, ancient galaxy, whether it is the oxygen found in the high-redshift system JADES-GS-Z14-0 or the carbon dioxide dominating the inner regions of the protoplanetary disk Shu-10, tells a story of cosmic inheritance. This chemical recycling process is what links human being directly to the deepest deep-field images captured by our telescopes. The carbon in our cells, the iron in our blood, and the oxygen we breathe were all forged in the nuclear furnaces of generations of massive stars that lived and died billions of years ago. By revealing that this heavy element production was already well underway within the first few hundred million years, modern astronomy shows that the universe became chemically capable of building complex structures far sooner than we ever dreamed possible. This accelerated timeline reshapes how we view humanity's place within space and time. For a long time, it was assumed that the conditions necessary to support complex planetary environments were rare, late-stage developments that required nearly 10 billion years of slow cosmic cooking to mature. But if the early universe was a hyper-efficient furnace, rapidly synthesizing heavy elements, stabilizing volatile atmospheres, and threading intergalactic space with structured magnetic networks, then the pathways toward structural complexity were open almost from the beginning. We see this ongoing evolutionary drama reflected in the behavior of our immediate galactic neighborhood. When we look at Sagittarius A star, the 4 million solar mass black hole at the center of the Milky Way, we are looking at a modern, quiet remnant of that ancient high-energy epoch. By tracking its erratic brightness fluctuations and near-infrared flares during continuous 48-hour monitoring campaigns, astronomers are watching the final low-level chapters of a feeding process that used to shape entire galaxies. Similarly, our closest neighboring stellar system, Alpha Centauri, continues to remind us that planetary systems are dynamic, evolving environments. The ambiguous, shifting mid-infrared signals detected near Alpha Centauri challenge our ability to easily categorize nearby worlds, highlighting just how much remains hidden in our immediate cosmic backyard. Whether these signals represent a forming planet temporarily masked by dust or a dynamic exozodiacal debris ring, they prove that the laws of planetary chemistry and orbital mechanics are continuously generating unique, localized surprises. The universe revealed by modern astronomy is not a static mechanical clockwork operating under rigid, predictable boundaries. It is a deeply interconnected, evolving macro system. It is a cosmos where the massive filaments of the cosmic web guide the flow of matter across hundreds of millions of light years, while individual magma worlds like 55 Cancri E continuously rewrite their own atmospheres through internal geological vitality. Understanding this larger cosmic story requires a profound sense of intellectual humility. It reminds us that we are a deeply curious species of cosmic infants, standing on a small rocky outpost, peering through a thin envelope of sky, trying to decode the rules of an ancient and beautifully complex reality. Every unexpected observation, every Super Eddington feeder, and every anomalous binary object is not a failure of science, but a gift to our collective imagination. They are invitations to abandon our oversimplified assumptions and adapt our understanding to match the rich, dynamic cosmos as it truly exists. As we look toward the future, the horizon of observational astronomy has never been more vibrant or promising. The remarkable data streaming back from our newest space telescopes demonstrate that our journey to understand the cosmos is a continuous, unfolding adventure. Every unexpected discovery, every early massive galaxy candidate, And every Super Eddington black hole recites us that the universe is far richer, more dynamic, and more efficient at organizing matter than our previous, oversimplified models could have ever predicted. These revelations do not signify a crisis in physics. Rather, they mark the threshold of a monumental leap forward in humanity's collective understanding of space, time, and cosmic structure. We are incredibly fortunate to live in an era where the deep mysteries of the ancient universe are actively being decoded week by week, image by image. As our technology advances and our computer simulations evolve, we will undoubtedly uncover even more refined layers of cosmic history, beautifully sharpening our map of the primordial sky and deepening our appreciation for the intricate natural laws that govern reality, from the grandest cosmic web down to individual localized worlds. If you enjoy exploring these profound cosmic mysteries, following the verified scientific evidence, and journeying to the very edge of modern astrophysics, please consider supporting this channel. Take a moment to hit the like button, subscribe to stay updated on future scientific discoveries, and share this video with fellow space enthusiasts. We would love to hear your thoughts on these new discoveries, so please leave a comment down below. How do you feel about the hyper-efficient complexity of the early universe? And what aspect of these high-redshift anomalies fascinates you the most? Thank you deeply for watching, for staying endlessly curious, and for participating in this historic golden age of astronomy. Keep looking up, keep questioning old assumptions, and we will see you in the next deep exploration of our extraordinary cosmos.